Medic Mind. Motivate, mentor, maximize.
Welcome to Physics Lesson 7, Current and Voltage. This is the second lesson on electricity. In the previous tutorial, we looked at electric charge. Now we will look at current and voltage, the main topic in electricity. Having a look at the breakdown, we can see that there have been many questions on circuit diagrams and on voltage, current and charge. And in this tutorial, we'll cover the first 4 bullet points. To begin with, we'll have a look at conductors and insulators. So first of all, let's understand what current means. A current is a flow of charge, and this flow of charge is in the form of electrons. Metals are very good conductors of current, whereas non-metals are very poor conductors. Metals make very good conductors because they have delocalized electrons, which are free to move throughout the structure of the metal. And these electrons can flow through and cause a flow of charge, a current. Non-metals are poor conductors, or insulators, because the electrons are fixed in place and are not delocalized. We'll now look at current and charge. So as we said, current is a flow of charge or electrons. If you have an ordinary metal wire without a cell or battery, the electrons would move randomly and there would be no net flow of charge. However, when you connect a cell or battery, a voltage, the electrons will move in a certain direction, away from the negative terminal and towards the positive terminal. And this leads to a net flow of charge, which is an electric current. Therefore, we can see that a voltage is needed to create a current through a circuit. There's no point having lots of delocalized electrons in a metal wire if there's no voltage applied, because a voltage is required to make sure the electrons flow in a certain direction and ensure that there is a net flow of charge. But what does the value of current mean? Because we've defined current to be a flow of charge. We also define current numerically. For example, we might say that the current is 2 amps. Well, the value for current in amperes is the rate of flow of charge. So whilst current as a noun is a flow of charge, the value for current numerically is the rate of flow of charge. The current tells us how fast the charge is moving through the circuit. So as current is the rate of flow of charge, we can make an equation linking charge and time. Current equals charge over time. Current is measured in amperes, whilst charge is measured in coulombs. 1 ampere would mean that 1 coulomb of charge is travelling per second. A current of 5 amperes means that there is 5 coulombs of charge travelling per second, and so on. Let's have a go at a worked example. Calculate the charge flowing through a circuit in 10 seconds if the current is 2 amperes. Pause your video now and have a go yourself. Here, we can rearrange the pink formula at the top and make it charge equals current times time. We know the current is 2 amperes and the time is 10 seconds. So 2 times 10 equals 20 coulombs, which is our charge. We will now move on to voltage. We mentioned earlier that cells or batteries are required to pump charge around the circuit. They are almost like electron pumps. The cells or batteries transfer energy to the charge as it passes in the circuit. The energy given to the charges is measured in volts. We can define voltage, or potential difference, as the energy transferred per coulomb of charge that passes. It's measured between 2 points in a circuit. So as each coulomb of charge passes the component, the voltage tells us how much energy is being transferred. However, voltage can have a different meaning for a cell or battery compared to a component such as a lamp. For a cell, the voltage tells us the amount of energy given to the charge as it passes along. For a component such as a lamp, the voltage is a measure of the amount of energy taken from the charge by the component. If it's a lamp, it's the amount of energy taken from charge to produce light. So cells and batteries are continuously transferring energy to the charge, whilst the components are taking energy away from the charge. And in any circuit, the total amount of energy or voltage given to the circuit from cells or batteries equals the total amount of energy used up by the components within the circuit. We can measure voltage using voltmeters. Remember, a voltage for a component or a cell is the energy transferred per coulomb of charge. The voltmeter therefore has to measure the energy transferred. So, to measure any energy transfer, you have to measure the energy before and the energy after. And that is why a voltmeter has to be connected in parallel, because the voltmeter measures the energy before the component and the energy after the component to compare the difference and find out how much energy has been transferred. This particular diagram shows 1 coulomb of charge travelling around a circuit. There's a voltmeter connected opposite a cell, another voltmeter opposite a motor, and another voltmeter opposite a lamp. The voltmeter opposite the cell is measuring the amount of energy given to this coulomb of charge as it passes. The voltage is 6 volts, which means that 6 joules of energy is given to this single coulomb of charge. The voltmeter is measuring the difference in energy from 0 joules before to 6 joules after to work out the voltage. At the lamp, the voltage is measured as 4 volts, which means that there's 4 joules of energy transferred per coulomb of charge. There's only 1 coulomb of charge, so this means that 4 joules of energy are taken from this coulomb, which means that there are 6 joules before and 2 joules after. Therefore, 4 joules are used up. Here, the 4 joules are being converted to other forms of energy, such as light and heat. As the charge continues, the last 2 joules of energy are used at the motor. The motor is transferring 2 joules of energy per coulomb. This energy is transferred into sound. And finally, the coulomb is left with 0 joules of energy and returns back to the cell, where it regains 6 joules of energy. As you can see, the voltage of the cell is always split amongst the components. The 6 volts input from the cell is split between the lamp and the motor. Therefore, none is left over, and this is always the case for a circuit. The voltage input is equal to the voltage output. Whilst we can use voltmeters to measure voltage, we can similarly use ammeters to measure current. Current is measured in the form of amperes. 1 amp means that 1 coulomb of charge is travelling per second. Remember, current is the rate of flow of charge. The current flowing through a component is measured by the ammeter, and ammeters are connected in series, in line with components. Whereas remember, voltmeters are connected in parallel. Whilst voltmeters are measuring the difference in voltage between 2 points, ammeters can just measure the current in a particular point. In a series circuit, the current is the same everywhere, so you can place the ammeter anywhere in the circuit. For a parallel circuit, the current can vary, but within a single branch, the current will always be the same within that one branch. However, the current of each branch might vary, so therefore you would need an ammeter for each branch if you wanted to work out the current for each individual branch. This is a nice table just comparing voltmeters and ammeters. Voltmeters are connected in parallel, ammeters in series. Voltmeters measure voltage in volts, whereas ammeters measure current in amperes. 1 volt means 1 joule of energy is transferred per coulomb of charge that passes. 1 amp means 1 coulomb of charge is flowing per second. And below we can see the circuit symbols for the voltmeter and ammeter. We will now look at resistance. The resistance in a circuit slows down the flow of charge, the current. Resistance is working against current. For any given voltage, a higher resistance would mean a slower flow of charge and hence a lower current. So current and resistance are often known to be working against each other. You can find resistance throughout a circuit. You can have actual resistors, which are components designed to provide resistance in a circuit. On top of that, you can find resistance in all components. Wires, lamps, motors, and other components all have some elements of resistance. We measure resistance in ohms. We can measure resistance of a single component by looking at the current that flows through it in amps and the voltage applied across its ends in volts. The higher the resistance, the lower the current for any given voltage. Therefore, we can set up this very important equation. Voltage equals current times resistance. Often, this is known as V equals IR. V for voltage, I for current, and R for resistance. This is a very important equation to memorize, and will come up commonly in calculations involving electricity in the BMAT. Let's have a go at this worked example. A series circuit has a lamp, an ammeter, a 4 ohm resistor, and an 8 volt cell. Assuming the lamp and ammeter are resistance free, what is the current on the ammeter? Pause the video and have a go yourself. So we can apply the equation voltage equals current times resistance. However, we need to rearrange this because we know the voltage to be 8 volts and we know the resistance to be 4 ohms. Therefore, we can work out the current to be 8 divided by 4, which is 2 amps. We'll now look at series circuits. And we'll go through some certain rules for series circuits before having a look at parallel circuits. In series circuits, all components are connected in line with each other. And this means that voltage is shared amongst components. The voltage comes from the battery or cell. If the battery or cell provides 6 volts of energy and there are 2 identical lamps with equal resistance in the circuit, each lamp will get 3 volts. The second rule, current is the same in all parts of the circuit. You can calculate the current by dividing the total voltage of the battery or cell by the total resistance in the circuit. Current is not used up along the circuit, and that means that you can add an ammeter anywhere in the circuit. The current will always be the same. Rule number 3. The total resistance is the sum of the resistances of all components. The current needs to be the same everywhere. So the higher the resistance of an individual component, the greater its share of the voltage. So that current, which is voltage divided by resistance, stays the same. Therefore, if you add an extra lamp to a series circuit, the total resistance increases and hence the current decreases. All the lamps become dimmer. To work out the total resistance, we add up the resistance of each individual lamp, as we mentioned. So if you have two lamps, each with 2 ohms resistance, the total resistance would be 4. In this scenario, each lamp has the same resistance, so therefore, each lamp would get an equal share of voltage. However, if one lamp had a much higher resistance than the other lamp, the lamp with the higher resistance would get a higher voltage to make sure that each lamp has the same current flowing through it. Rule number 4. The cell voltages sum together. So if you have two 3-volt cells, the total voltage will be 6. If you have 3 2-volt cells, the total voltage will be 6. If you have 4 3-volt cells, the total voltage is 12, and so on. And fifth, a break in one component ruins the whole circuit. There is only one route for charge, so if one lamp in a series circuit is broken, all lamps will stop working. There is the classic question about Christmas lights and why they are often connected in series. However, if there is a break in one Christmas light, then all of the lights break. Whereas in a house, lighting is often done in parallel. And in parallel circuits, if one lamp breaks, the current can still pass through alternative routes, so therefore all lamps don't turn off. Let's have a look at this diagram. In this circuit, the voltage of 6 volts all goes to the single lamp. There is one cell giving 6 volts of energy, one lamp with a resistance of 2 ohms, and an ammeter, which we assume has no resistance. The current will be equal to the voltage of 6 divided by the resistance of the whole circuit, which is 2, only coming from the lamp, so the total current is 3 amps. Now we have added in an extra bulb of the same resistance of 2 ohms. Now the total resistance of the circuit becomes 4. Therefore, the current falls to 6 divided by 4, which is 1.5 amps. Both lamps therefore become dimmer. Each lamp gets an equal share of the 6 volts because they both have the same resistance. Here we've added in a third lamp. However, this third lamp has a much higher resistance of 4 ohms. Again, let's add up the resistances of each individual lamp to work out the total resistance of the circuit. The total resistance of the circuit would be 4 plus 2 plus 2, which is 8. And the voltage remains at 6, so the current will be 6 divided by 8, which is 0.75 amps. However, the share of voltage amongst the lamps is no longer even. It's not a case of dividing 6 by 3 and giving each lamp 2 volts. We need to make sure that each lamp has 0.75 amps traveling through it. So for each individual lamp, you can take its resistance and take the value of 0.75 amps and therefore work out its voltage. So the voltage of the 4 ohm lamp would be 0.75 times 4, which would be 3 volts. And similarly, for the 2 ohm lamps, the voltage would be 0.75 times 2, which is 1.5 volts. And finally, in this circuit, an extra cell has been added. And as we explained before, the cell voltages can add up together. So there are two 6-volt cells which add up to a total cell voltage of 12 volts. Therefore, the current is now 12 divided by 8, which is 1.5 amps. We will now move on to parallel circuits. In parallel circuits, the components are connected on separate loops. This means that first of all, the voltage is the same for all branches. When we looked at series circuits, we saw that the voltage was shared between the components in proportion of their resistance. In parallel circuits, every branch gets the full maximum voltage. In this example, there are two bulbs, and each branch has just one bulb. Therefore, each bulb gets the full maximum voltage of 6 volts. The second rule is that the current is split between the branches of the circuit. In this circuit, we can see that there has been an extra bulb added to one of the branches. This means that the voltage of 6 volts is split between the two bulbs for that particular branch. Remember, each branch gets the maximum voltage of 6 volts. However, within the branch, we can split the voltage like we would in a series circuit, because the two bulbs in the first branch are in series to each other. Therefore, they split the 6 volts between them equally because they have equal resistance. The overall current in that branch is 1 amp, whereas the overall current in the other branch with only one lamp is still 2 amps. The branch with the two bulbs has a higher overall resistance and therefore has the lower current. The third rule is that total resistance is worked out using the reciprocal of the resistances of each branch. So if there are 3 branches to the circuit, R1, R2 and R3, then we can say that 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. According to the BMAT specification, you don't need to know specifically about the resistance in parallel circuits. It's useful to memorize that you calculate it using the reciprocals, but you won't have to do any calculations based on this, so don't worry about it too much in your revision. Next, we'll have a look at energy transferred by components. All components transfer energy using the current that flows through them. Lamps can transfer energy into light and heat. Motors can transfer energy into sound. Resistors can transfer energy into heat. And of course, some of this energy will be useful and some of it will be a waste. For example, for a lamp, light energy is useful, but heat energy is a waste. Earlier, we defined voltage as the energy transferred per coulomb of charge that passes a component. Therefore, to find the total energy transferred, we need to multiply the voltage, which is the energy per unit charge, by the amount of charge. Therefore, we can say that the energy transferred equals the voltage times charge. Just to recap once more, the voltage is the energy transferred per coulomb of charge. So therefore, if you multiply the energy per coulomb by the total number of coulombs, the charge, we can work out the total energy transferred. Bear in mind that this includes both useful and wasted energy. So for the lamp, this would tell us the amount of light energy plus heat energy. And therefore, we can work out percentage efficiency by comparing the useful energy output and the total energy output. Additionally, for a cell or battery, we can look at the energy transferred to the charges as they pass. Because remember that cells and batteries give energy to charges, whereas components such as lamps and motors take away energy from chargers. To finish this tutorial, we'll have a look at circuit symbols. Pause the video and try to name the circuit symbols shown here. The first symbol is a switch, an open switch. The second symbol is a cell, and the third symbol is a battery. Have a go again. The first symbol is a lamp, the second symbol is a voltmeter, and the third symbol is an ammeter. Have a go again. The first symbol is a resistor, the second symbol is a variable resistor, and the third symbol is a motor. A variable resistor is a resistor which can be adjusted, so you can adjust the amount of resistance in the circuit. We will now move on to a few questions to finish the tutorial. Pause the video and have a go at this question. The answer here is D. First of all, let's work out the voltage of the circuit. We know the current and the resistance for the first branch, which has the 20 ohm resistor. We can use the equation voltage equals current times resistance. We know that the current is 0.3 amps in the first branch and the resistance is 20 ohms. So therefore, voltage will be 0.3 times 20, which is 6 volts. Straight away, we can knock out A, B, E, and F. Now, we know the resistance to be 10 ohms for the second branch, and we know that the second branch will have the same maximum voltage as the first branch, which would therefore be 6 volts. So therefore, we know the voltage to be 6 volts, and we know the resistance to be 10 ohms. Therefore, we can rearrange V equals IR to make V over R equals I. So voltage divided by resistance equals current. 6 divided by 10 equals the current of 0.6 amps. So therefore, the answer is D. Let's have a go at question 2. Pause the video and have a go by yourself. The answer here is E. Statements 2, 3, and 4 are correct. Let's go through each statement one by one. With this circuit, we can straight away see that there is possibilities for short circuits to appear. Short circuits occur when current can bypass components and take a path with less resistance. So for example, if switch P was closed, the current would bypass lamp A because the lamp has more resistance than an empty wire. Similarly, if Q was closed, the same thing would happen for lamp B. Now let's apply this to each individual statement. Statement 1. When switch P is closed and Q is open, the current in the circuit is 2 amps and only lamp B is lit. Well, when switch P is closed, the current will bypass lamp A, so therefore only lamp B would be lit, which is correct. Q is open, so lamp B would not be bypassed. However, the current would be 4 amps, because there's only one lamp in the circuit therefore. You have only lamp B, which has a resistance of 3 ohms. And the overall voltage is still 12 volts, so using V equals IR, we can divide the voltage of 12 by the resistance of 3 to give 4 amps. Number 2. When switch P and Q are both open, the current in the circuit is 2 amps and both lamps are lit. Well, in this case, there are no short circuits and the resistance is 6. Therefore, voltage of 12 divided by resistance of 6 gives you a current of 2 amps. Statement 2 is correct. Statement 3. When switch Q is closed and P is open, the current in the circuit is 4 amps and only lamp A is lit. This is similar to statement 1 but is reversed around. In this case, Q is closed and P is open. And unlike statement 1, they have got the correct current of 4 amps. Statement 4. When switches P and Q are both closed, neither lamp is lit. This is correct. There is a short circuit. So therefore the answer is E. Let's have a go at the next question. Pause the video and have a go. The answer here is B. This might seem like quite an unusual question because you're used to the unit of voltage being the volt. However, what this question is asking you to do is use different equations and rearrange them and combine them together to get an equivalent voltage unit. We know that voltage is current times resistance, and we also know that current equals charge over time. So therefore, we could substitute current into the V equals IR equation to give us voltage equals charge over time times resistance. Therefore, voltage equals charge times resistance over time. Charge is measured in coulombs, resistance is measured in ohms, and time in seconds. Therefore, voltage equals coulomb times ohm over second, which is correct. For these types of questions, the best approach is to write down the 2 to 3 equations you know relating to electricity, and then try to rearrange them to find one of the answer options. Let's have a go at the next question. Pause the video and have a go. The answer to this question is E. Statements 3 and 4 are false. Be very careful. This question is asking you to choose the false statements, not the true ones. Statement 1 is true because each branch of a parallel circuit does receive the maximum cell voltage in a parallel circuit. Number 2, within a branch of a parallel circuit, the current is always the same. And this is correct. Within a branch, you almost have a series circuit, and therefore the current is always the same. The current might vary between branches of a circuit, if it's in parallel, but within each branch the current will always be the same. 3. In a parallel circuit with multiple bulbs, if one breaks, none of the other bulbs will be affected. Well, in a series circuit, we know that this would definitely be false. For a parallel circuit, this might not be the case. However, the statement is very extreme. It is said that none of the other bulbs will be affected. There could be a chance that other bulbs will be affected, because if there are bulbs within the same branch as the broken bulb, there will be other bulbs affected. Therefore, it's premature to say that none of the other bulbs will be affected. 4. The total resistance in parallel circuits is the sum of the individual resistances of all components. This is incorrect because it's the reciprocal of the resistance, which is the sum of the reciprocals of the individual resistances. Therefore, the answer is E. And on to our last question, 5. Pause the video and have a go. The answer here is F. Let's look at each scenario. Initially, switch Q is closed. This is another example of a short circuit. The current would pass through lamp C but bypass A, B, D and E as it passes through Q. However, switch Q is now opened. Now the current has to pass through A, B, D and E, and it acts like a normal parallel circuit. Therefore, A, B, D and E all get brighter. Lamp C still has the current flowing through it. However, there are now 5 lamps involved in the circuit as opposed to 1 when Q was closed. Therefore, the total resistance will be increased for the circuit, and therefore the overall current in the circuit will be lower. So lamp C would have a lower current flowing through it, and therefore lamp C would be the dimmer brightness. Thank you for watching this tutorial on current and voltage.
Thank you for watching this free BMAT tutorial from Medic Mind. To unlock the rest of the 100 tutorials and all 8 ebooks, click here now.